Welcome, ladies and gentlemen, to another lecture on solving problems using conservation of energy. Today I'd like to take a closer look at conservation of mechanical energy by solving some problems using this tool. Okay? So we're just going to solve some more problems just like we did in the last lecture. So our first problem here. Consider a spring-powered Nerf gun. I want the speed of the 35-gram Nerf ball to be 11 meters per second, and the mechanism is designed to compress the spring by 10 centimeters. Assuming no non-conservative forces, what should the spring constant be of the what should be the spring constant of the firing spring? So let's draw this. We have a spring. It's compressed by some distance x. We have this little Nerf ball. It has a mass m. And we know that m equals 0.035 kilograms. We know that x equals 0.10 meters. And then we want to know what k equals. Okay? And this is a potentially real-world problem, right? If we're making a little Nerf gun, we probably want to have the little Nerf ball that comes out have some maximum velocity because that's probably a safety concern, right? If we shoot it too fast, it starts to become unsafe. So we have to keep it at a certain speed. But we want it to be fast enough that it's fun, right? The ball can't just fall out of the end of the gun. It has to shoot out there with some velocity so that it's fun to use. And so we want to dial in our spring constant on whatever spring we use when we build the toy to kind of fit these speed requirements that we have for the ball. Okay? All right, so we're going to solve this problem with conservation of mechanical energy. Again, today we're solving all the problems with this, but in general, we would want to choose this anytime it's a viable technique, okay? Again, because it's easy. We like when we can use easy things. All right, so then we just look at each term. In the beginning, do we have a potential energy? We do, right? The spring is compressed. 1/2 k x squared. Okay, do we have a kinetic energy at the beginning? No, the ball's just sitting there in the gun. Do we have any non-conservative forces? No, the problem said don't worry about any non-conservative forces. Is there potential energy at the end? No, the spring is back to its equilibrium point at the end, right? When it shoots the ball, it's done. Is there kinetic energy at the end? Yes, the Nerf ball has 1/2 mvf squared kinetic energy. Okay, then algebra. We just do algebra and solve for k. K equals mvf squared over x squared. Okay, there's our answer. We're already done. Units. We have kilogram, meter squared, per second squared, meter squared on the bottom. Okay. And then if I use just 1 meter from the bottom to cancel 1 meter from the top, what I would end up with is a Newton. I'd have a kilogram meter per second squared over a meter, right? And that is the unit of a spring constant, okay? Newtons per meter. Sanity. K is bigger as m is bigger. So if we shoot a heavier Nerf ball, we need a stronger spring to shoot it at the same speed. Makes sense. K is bigger as Vf is bigger. So if we want to shoot the same size Nerf ball at a faster speed, we need a stronger spring. That makes sense. K is smaller as x is bigger. Okay? So if we have the same spring, but we're going to compress it even further, then we don't need the spring to be as powerful, right? So if we're going to make this distance x this big, we don't need as strong a spring because we have a bigger distance that we can apply the force over. That makes sense too. It obeys Hooke's law, right? Okay. So everything makes sense. Everything looks good. And then if we plug in numbers, k equals 420 newtons per meter. Okay, 2 sig figs from our stuff up here. All right, let's look at our next example. So, much like our example of the bow, let's consider a trampoline as obeying Hooke's law. If I have a mass of 100 kilograms and jump off of a roof and fall 5 meters, landing in the middle of a trampoline with an effective spring constant of 1150 newtons per meter, how far down will I push the middle of the trampoline? Okay? So I'm up on this roof. It has some height h. I'm going to fall down onto this trampoline. Okay? H is 5 meters. K for the trampoline, the middle of the trampoline where I'm going to land, is 1150 newtons per meter. Okay? And then the question is, when I compress the trampoline, so when I land on it, and it looks like this, what will this distance d be? Oh, and I have a mass of 100 kilograms. Okay, so we're going to solve this with conservation of mechanical energy. So at the beginning, is there a potential energy? There is, right? It's mgh. At the beginning, is there a potential? Is there a kinetic energy? No, I'm just standing on the roof. No kinetic energy. Is there non-conservative work being done? No, we don't have any non-conservative forces in the problem. Okay, that's equal to, at the end, is there a kinetic energy? Yeah, it's 1/2 k d squared, right? However far down I displace the middle of the trampoline. Okay, this distance d. At the end, is there a kinetic energy? So it's important to recognize on this one, at the end, there isn't a kinetic energy, right? Because if I'm still moving at the end, either I'm going to keep pushing the trampoline down, right? So I'm pushing the middle of the trampoline down like this. Well, if I'm still moving, then I'm still pushing it down and I haven't reached the bottom yet, right? Or if I'm moving back up, then I've already reached the bottom and the trampoline is now pushing me back up. Okay? So right at the very bottom, the lowest that the trampoline reaches, I have a velocity of 0. Okay? Just for that moment in time, that instant when the trampoline is at its most depressed, I have a velocity of 0, so this kinetic energy is also 0. Okay? But once I can make that conceptual recognition, right? Like once I realize that that's the case in this problem, then again, it's basically free to solve it, right? Again, it's really easy. 2 mgh over k in a root. Oh, I forgot the g. I said it, I didn't write it. mgh over k. All right? That was it. So the hardest part of that one was just conceptually recognizing that if it's at the very bottom of how far I push down the trampoline, there's no kinetic energy. Once I recognize that, this problem's easy peasy, lemon squeezy. The units, we have a kilogram meter per second squared times a meter. And then we have on the bottom here K, which is newtons per meter. This piece is a newton, right? And this is a newton. This was all in a root. So I have meter squared, the square root of meter squared, which is meter. And then sanity. We have if my mass goes up, D goes up, right? So mass goes up as, or D goes up, sorry, as mass goes up, right? That makes sense, right? The fatter I am, the more I push the middle of the trampoline down. D goes up as G goes up. That makes sense too, right? The bigger my acceleration is, the faster I hit the trampoline initially, and the more kinetic energy this spring has to take out of me, okay? So I'll press it down further. D goes up as H goes up. So if I jump off something higher, I'll press down the middle further. That makes sense as well. And D goes up as K goes up. Or sorry, D goes down as K goes up, right? We have K in the denominator of our fraction here. So D goes down as K goes up. So again, the middle of the trampoline won't push down as hard if the effective spring of the trampoline, we're modeling it as acting like there's a spring under me right here, right? If that effective spring is stiffer, I won't press it down as far. That makes sense too. Okay? And then if we plug in the numbers, I believe we find that D equals 2.9 meters. And 2 sig figs coming from this guy right here, right? Okay, now let's look at our last example here. A 1,200 kilogram car starts from rest. Then I push it with a force of 1,800 newtons parallel to the flat ground over a distance of 4 meters. How fast will the car be going at the end of this push? So we have a car. Car has a mass of 1,200 kilograms. Okay, I'm going to push it with a force of 1,800 newtons. And I'm going to push it over some distance, x, where x equals 4 meters. And the question is, how fast will it be going at the end of this distance? Okay? Okay, so we're going to solve this with conservation of mechanical energy. Okay, so we start from here. We ask ourselves in the beginning, is there a potential energy? No. This time I have the car on flat ground, so there's not going to be any change in height, right? So I don't have gravitational potential energy. It's not connected to a spring or a rubber band or something like that that's elastic. I don't have any elastic potential energy. So this term is 0. Does it have any kinetic energy? Well, it starts from rest, right? Rest means velocity is 0, so kinetic energy is 0 at the beginning. And then am I going to do non-conservative work on it? I am, right? The force of my push is a non-conservative force on the car, okay? So I'm going to have to figure out the work that I do on the car. So W and C equals the force of the push dotted with the displacement, okay? Now, the displacement is along the ground, and the force of the push is parallel to the ground. So this dot product just becomes FPX, okay? Because this is FPX cos theta, where the angle is the angle between FP and X, right? But theta equals 0, and cos 0 is 1. And then I was actually given the force of the push. So I don't need to solve for anything else, right? I was given the force of the push. I was given the displacement x. So I just know those things, okay? So in my conservation of energy equation, Fpx equals potential energy at the end. Again, this is 0. And then kinetic energy that I've given the car by way of my non-conservative work. Okay? And once again, all the work of the problem was in just applying our physical principles correctly. And now the algebra of the problem is incredibly simple. And we have 2 Fpx over m in a root. Okay? Units. We have newtons times meters over kilograms in a root. Remember, this means that we have kilogram meter per second squared times meters over kilograms, all in a root. And I have meters squared per second squared in a root, which means I have meters per second. sanity. VF is bigger as FP is bigger. So if I push harder, I can make the car go faster. That makes sense. VF is bigger as X is bigger. If I push the car with the same force, but I push it for a longer distance, I can make it go faster. That makes sense too, right? When I push on it with some force, I give it an acceleration. And the longer distance I apply that acceleration over, the faster the car will be going. And then VF goes down as M goes up, okay? So if I'm pushing a Mini Cooper, I'm going to give it, if I'm pushing it with the same force, right? My force is fixed. If I push a Mini Cooper with the same force, I'll give it a bigger speed than if I push, I don't know, a Ford F-250 with the same force, right? The Mini Cooper weighs probably less than half of what the truck weighs. That makes sense, right? The car, if it has a much bigger mass, I can't push it as fast. That makes sense. And then if we plug in numbers, we find that we have 3.5 meters per second. So that concludes our lecture for today. You guys will have a chance to practice using this tool some more on additional homework that comes with today. And hopefully by this point, you've realized what a wonderful tool this is and how useful it is for us to solve problems that deal with a really wide array of physical systems, and just how convenient it is to use this tool. As we move forward, we're going to start looking at conservation of momentum, which will expand our ability to describe physical systems even further.